Our second keynote speaker is Dr. Ioana Dumitriu. She received a Bachelor of Arts in Mathematics from New York University in 1999 and earned a PhD in Applied Mathematics from the Massachusetts Institute of Technology in 2003. Following a Miller Research Fellowship at the University of California, Berkeley from 2003 to 2006, she became a regular faculty member in the Department of Mathematics at University of Washington, Seattle, spanning 2006 to 2019. She joined the University of California, San Diego in 2019. Dr. Dumitriu's research spans a number of areas that fall under the large umbrella of data science, from numerical linear algebra and scientific computing to stochastic eigenanalysis, also known as random matrix theory, and from discrete probability and spectra of random graphs to applications in machine learning, specifically to clustering and community detection. Dr. Dumitriu has been the recipient of many honors. She is a fellow of the American Mathematical Society and has received the National Science Foundation Career Award. Dr. Dumitriu is the winner of the Leslie Fox Prize in Numerical Analysis, an award given to a young numerical analysis researcher who excels both mathematically and in presentation skills. She is also the recipient of the honorable mention for the Householder Prize in Numerical Linear Algebra. Please join me in welcoming another Math Prize for Girls Board of Advisors member, Dr. Ioana Dumitriu, who will speak to us about Playing 20 Questions with a Liar, a window into basic coding theory.
Thank you very much for this introduction that makes me blush. And I have to say that I'm extremely honored to have been invited to give a talk today and to be in the presence of such distinguished faculty members and mathematical organization leaders, and in the presence of so many. I can look at the number of participants and it's tremendous. So many aspiring mathematicians, I would like to hope, and talented young girls who are interested in math. It is really a great honor to be here. And it is also an honor to give a talk under the title of, or rather, an address that is titled using Mariam Mirzakhani's name. I intersected briefly with Mariam when she was a student. I was a student at MIT, she was a student at Harvard, but she had friends at MIT. And so I got to see her from time to time, and she was tremendously impressive. And it's such an honor to have known her. Okay, so my talk today is going to be a little bit lower tech than Dana's. By the way, I enjoyed your talk tremendously, Dana. It was wonderful. And I have to say that I was thinking when you mentioned that you first started thinking about doing research at Bell Labs, and the amount of stuff that you learned from your mentor there, that I suspect that mentor was Peter Winkler. And no, he wasn't, but he had a lot of good things to talk about you, to say to me about you when he was my mentor at Bell Labs. So we have that connection together. It's such an important thing to have good mentorship. And that's something that I think most of us are trying to offer because we've benefited from it. So my talk is going to be a little bit lower tech. I'm going to try and share my screen, and then please let me know if you can see my talk. Let me go to full screen mode. This has not worked very well in the past, so if it doesn't work, please let me know. Does it look okay? Can you see it? Yeah, okay, good. All right, so I'm going to go a little slowly, and we're just gonna start by playing a game. This is a soft introduction into what can be, what it can mean to do research in very basic coding theory, and what kind of things you can see when you try to use math to answer questions that are actually practical questions or that are real world related. There's also always a little amount of like idealization, because you know the joke about the spherical cow, I guess. So all right, so without further ado, let me just talk about this game that I want to present to you, playing 20 questions with a liar. So you know what 20 questions is like. It's a very popular game. You generally ask yes or no questions to find either an object or an idea or a concept. And, you know, the rules are preset. You know what you're allowed to ask, but the answer will always be yes or no. So it's a binary game. Now, today, there's always a limited number of questions, obviously. In principle, well, although I should say that in my household we play infinity questions mostly with my two kids, because 20 questions can be quite restraining, especially when they're young. So, but for practical purposes, let's assume that this number is set, say like a 20. But today, instead of searching for an object or an idea, we're going to try and find a number. So here's an example. How many questions do you need to find a number between 1 and 8? I'm fairly certain that all of you know the answer. The answer is, of course, 3. And the questions are of the type, is the number in the set 1 to 4? Okay, so you can give a set of numbers from 1 through 8, and the answer is going to be yes or no. Is the number in this set, or is it not? And after the right 3 questions, we always know the number. The trick, as always, is to take your set of, in this case, 8 numbers from 1 through 8, and ask a question that halves the numbers of possibilities at each step. So you go from 8 possibilities to 4 possibilities to 2. And then finally, when you have 1, you know what the number is. Okay, so what about if the number is between 1 and 1024? Of course, 1024 is 2 to the 10. You do the same thing. You apply the same trick of always cutting in half the number of possibilities. You can say, for example, is the number in 1, 2 through 512? And if the answer is...
Sorry, excuse me, Ioana. I just see the title slide. Have you moved past the title slide?
Yes, I have.
Okay, I think other people are only seeing this title slide too.
Afraid of that. Okay.
Oh, so that's better. Okay, maybe is that the second slide, or were there others?
There were others.
Okay. Yeah.
I'm not sure what I did wrong with
okay,
this.
well, now we can see it. That's good. Maybe just back up and...
Let's just go on from here. So okay. The idea of finding a number from 1 to 1024, keeping in mind that the number 1024 is 2 to the 10th. If you have a suggestion of how I might do this without this downside of not moving, of the slide not moving, if anybody has an idea of how to do that, I would be happy to entertain suggestions. I'm not, give me 1 second, I'll see if I can maybe. Okay. Sorry about that. Okay, for now, I'll just leave it like this. And if it doesn't work, please let me know. Okay, so the trick here would be to say, is the number between 1 and 512? And if the answer is yes, then those are the numbers you keep. And if it's higher than that, then it's the complementary set of numbers that you're going to keep. So you are going to need 10 questions to answer, to find, to locate this number between 1 and 1024. So let's turn this a little bit around and say, suppose that I give you a total of Q questions. Amongst how many numbers can you differentiate? And the answer is, of course, going to be 2 to the Q. So 2 to the Q is going to be the maximum number based on this strategy of always cutting in half the number of possibilities. One different way to look at this is to say that Q has to be the ceiling of log base 2 of n. Now, there's something to be said about expressing things in terms of n rather than in terms of q, but the issue is that can you see my cursor? When you express things this way, something may get slightly lost in the way, because it's in a sense, it's easier to talk in terms of Q because the answer is exact, whereas here you have to take a ceiling. And later on, when we're going to talk about what happens when N and Q are large, and we're going to talk about asymptotics, this is a slightly more accurate asymptotic than this, as we'll see. So this is the game with Q questions with no lies, and it is very well understood, and it is very easy to play. Okay, but keep in mind that by delaying the picking of a number, the person that you're playing with can employ an adversarial strategy, which means that they will answer consistently with at least one possible answer, and that they can force you to always use all your questions. Okay, so it's a much smarter, in a sense, strategy not to actually start out by picking a number, but by answering consistently with the largest number of possibilities that could remain, and so extend the game as far as you can. Okay, so, but what if I should decide to lie and not to tell you the truth once, twice, 3 times, or maybe in a certain way? Maybe I'm deciding to lie to you if you ask me a question for which the truthful answer ought to be yes, and I decide to say no, but I decide to always tell you the truth if you ask me a question with the right answer no. So there are many ways of lying, right? Suppose I decide to lie. And let's take a look at this twisted setup. And let's consider this a game between Paul, who is going to be the questionnaire, the guy who asks the questions, and Carol, who's going to be the answerer. And suppose that the idea is Carol chooses a number, and Paul must find it by narrowing the possibilities until only one single possibility is left. Now, same question as the one that I mentioned in the beginning. How many questions does Paul need to find a number between 1 and 8? But now allow Carol to lie and understand that the number of possible lies is important here. Okay? Suppose that you can lie once. You want to find a number between 1 and 8, and the person answering is allowed to lie once. Let's see how we might do that. Well, the first idea, which as always is almost always wrong, right, is that Paul can ask each question 3 times and then take the answer given at least 2 times. So do sort of a majority answer. Of course, that's very wasteful. You need at least 9 questions to employ this, and there's no need for it really, because you can do better and you need to do better. Okay, so you want to actually find a way to do it in a way that's efficient as much as possible. So here's a better strategy. Start in the same way by trying to eliminate half of the possibilities. So say you start asking, is it in 1, 2, 3, 4? So that's the first half of the set. But instead of dismissing half the numbers if the answer is yes or no, keep the other set around in case Carol lied. And you have to continue this after each question. So what does that mean? It means that to each number, we will associate a number of lies that Carol must have said in order for this number to still be a possibility. So you keep track of possibilities in a vector, counting, or rather associating every number to the number of lies that she must have said in order to make it still a possibility. So without loss of generality, let's assume that her first answer to this question is in 1, 2, 3, 4 is yes. That means that the possibilities now are going to be 1, 2, 3, 4 if she was truthful, but also 5, 6, 7, 8 if she already spent her lie. Okay, so in this way, we haven't eliminated anything, but we keep track of how many lies must have been uttered for a particular number to still be a possibility. Okay, so now let's go on and split, we're going to try and apply more or less the same kind of principle that we did before, which is split things equally. Okay, now we have 4 possibilities for no lies and 4 possibilities for 1 lie. So let's split things equally by picking 2 numbers from the first category and 2 numbers from the second category. So our next question is going to be, is it in 1, 2, first category, 5, 6, second category? And let's say that her answer is no. Her answer doesn't really matter because I'm assuming that she can lie equally on a yes or a no. And now let's see what the possibilities are. So we have 3 and 4 if she answered truthfully, and if she answered truthfully at the previous question. And if she answered truthfully at the first question and lied on the second, we still have to keep around 1 and 2. But now the vector has a 1 in second position because these are only available to us as possibilities if Carol lied. And similarly, now let's see, if she said no, it's not 5, 6, and she had lied before, then it's for certain no longer 5 or 6, sorry. It's no longer 5 or 6 because she said yes and no, so no, those numbers are eliminated. But 7 and 8 are still around because she said yes and she might have lied. And now if she said no, it's not 1, 2, 5, 6, then 7 and 8 are still possibilities. So this is what the set of possibilities looks like now. Again, we have 2 with no lies, 4 with 1 lie, and once again, we can use a question to split the set of possibilities equally. So we're going to split it as follows. And this is a recollection of what was on the previous slide. We split numbers now by picking 3 from amongst the 2 with no lies and pick 1 and 2, so 2 numbers from amongst the 4 where she already lied. And so let's ask the question, is it in 1, 2, 3? And assume the answer is yes. This is our third question. Then let's see, supposing she never told a lie, 3, 0 is still an option. And if she lied somewhere along the way, but told the truth now, then 1, 2 are still options with 1 lie. However, if she told the truth now, since she had, if she lied before, so if 7 and 8 were still possibilities, she must have told the truth now, so it's not 7 and 8, so those go away. However, if she told the truth up to this point, but lied now, that means that 4, 1 is also a possibility. Okay, so this is our field of possibilities right now. 3 if she didn't lie at all, and then 1, 2, and 4 if she lied once. Okay, so that's where we are. So our next question, we can no longer divide things perfectly. So I'm going to just pick 3 and 0 and 2 of the, and 1 of the other ones, the first one. And I'll ask, is it in 1, 3? And if the answer is no, let's see what we have. If the answer is no, then 1 is eliminated because this must have been a true answer with respect to 1. But if the answer is no, and it was 3, then I have to keep it around and mark the fact that she lied. Okay? And to look at the rest of the possibilities here, she must have answered correctly here. And so the 2 possibilities, 2 and 4, can still stick around in case she lied once. So now our field of possibilities has been reduced to 2, 3, 4, and she used her lie in any case, because at this point she has given enough answers that we know somewhere along the line she must have lied. There are no possibilities for her left where she didn't lie. And so at this point we have a simple, she's not allowed to lie, she's not allowed to lie anymore. So these three possibilities reflect from now on only truthful answers, and we're going to need 2 more questions to differentiate between them. So there are no lies left, and we can solve this with 2 questions. And we've used 6 questions to determine which number she thought about. It turns out this is actually optimal. And even though I've done this on a particular set of questions with a particular set of answers, you can actually do it in a more general setup. So let's explore this a little bit to understand what's going on. Suppose, again, I want to look at splitting possibilities as equally as I can. Okay, so with no lies, we only cared about this split, and it could be done almost perfectly all the time, but that cannot necessarily be done here. But you want to approximate that as much as you can. So you want to always ask a question that leaves roughly the same number of possibilities regardless of answers. And this is how it's done. If you have X numbers still possible if she lied once up to this point, and Y numbers still possible if she didn't lie at all, then what you want to do is ask a question that involves half of the numbers that are possible with one lie and half of the numbers that are possible with no lie. The trick is that afterwards, the outcome is always X plus Y over 2 possibilities for one lie and Y over 2 for no lie, and regardless of whether she says yes or no. Okay, so this is how this perfect or almost perfect split translates for the case of one lie. And it can be made completely rigorous. Okay, so here's how you would do it for n is equal to 8. We start with all the numbers in the no lie group. So we have 1, 0, 2, 0, 3, 0, up to 8, 0. Then you select 4 of them and ask. Regardless of the answer, 4 of them will be attached to one lie, 4 of them will stay the same. So when I say 8, 0, it means 8 with no lies, 0 with one lie. At the next step, we'll have 4 with no lie and 4 with one lie. Then you select 2 from each group. And regardless of the answer, at the next step, the situation or the number of possibilities is going to be 2 and 4. You'll eliminate 2 of these 4, and you'll transfer 2 of these 4 to the second column. Then you can select 1 and 2 again. You can split things perfectly. And now at the next step, the situation is going to be 1, 3, because you will eliminate 2 of these 4, and you'll move 1 of these guys to the second column. With 1, 3, you select 1 from each, and at the next step, you're either going to be at 0, 2, or 1, 1, and at most 2 more questions will suffice. So overall, you get these 6 questions that, as I said before, is optimal. So that's what you want to do for the case of one lie. Okay, and in fact, this can be translated into the following theorem. So if Paul gets Q questions and Carol gets to lie once, then if the number of possibilities that you start out with is less than or equal to 2 to the Q over Q, then Paul can always guess the number with Q questions. And if it's bigger, then Carol can prevent Paul from finding the number that she allegedly thought up before the game started by always giving answers consistent with the largest number of possibilities. So by employing this so-called adversarial strategy. And this is assuming perfect play for both of them. I mean, oftentimes in these two-person games, you'll have to assume perfect play, as in everybody has access to the exact total amount of information. And in this case, that means that Carol will delay her choice to prolong the game and reach the worst case scenario for Paul. And Paul asks questions consistent with this strategy for Carol. If she doesn't employ this strategy, then Paul will find the number faster. Okay, so how does this relate to coding theory? So in a very simplistic way, coding theory is a branch of computer science, theoretical computer science, which deals with bit transmission over a channel. Now, there are two types of channels that I pointed out to here. This is an X channel and this is a Z channel. An X channel corresponds to the possibility of a 1 becoming a 0 or a 0 becoming a 1, in addition to being communicated correctly. That means a 1 will become a 1 and a 0 will become a 0. And a Z channel corresponds to a 1 always having to be transmitted as a 1, but a 0 being transmitted either as a 0 or a 1. So these are binary channels because they are transmitting 0s and 1 bits. And they're faulty because in addition to the 1 goes to 1 and 0 to 0, which are the correct transmissions, you have these extra possibilities, these extra edges. Okay, so these are two channels through which bits can be transmitted in a faulty way. Okay, so X, as I said, allows for both false positives and false negatives, whereas Z allows for false positives, but not false negatives. Some medical tests and clinical tests can be this way. They can allow for either false positives, but no false negatives, or the other way around. So this is relevant in that sense. There are also much more complex channels possible when you don't transmit just 0, 1 bits. You can have some finite number of bits that are being transmitted, and the way to mess them up can be fairly arbitrary. So you can have a fixed number of possible faulty transmissions, which means an excess number of edges in the channel. So there are lots of other ways that you can generalize this problem and make it more grounded or more closer to what you would encounter in real life in channel transmission. Okay, so one of the main focuses of coding theory is to recover the correct transmission when you know that bits are potentially scrambled by a faulty channel. So this is one way in which you can see these liar games as a worst case scenario in bit recovery, where the channel is replaced by an opponent who will try to do their best to prevent you from finding out the true message that was communicated. Okay, so given a message M with n bits, how many extra bits do you have to send through the channel to make sure that the message is reconstructible? You can always reconstruct. The question is, how many extra bits would you have to do it? So it's a matter of efficiency. It's not just a matter of finding the right, finding an answer, but finding the most efficient answer. So let's reformulate this. If the opponent, or Carol, is allowed to lie a few times, how many extra questions will you need? And again, with variations. What if she has to tell the truth if the true answer is yes? And what if we have more than 2-bit values? So the answers turn out to be known in some sense for a lot of these problems. For the X channel, where you can lie equally, the answer is known exactly in terms of the number of questions and the number of lies that you allow. But the answer is only known asymptotically, meaning approximately, and for Q very large, for the Z channel, so where the lies are one-sided. Now, just to remind you of the notation, Paul must try to find a number between 1 and n with q questions, and we allow Carol to lie k times. And we saw the strategy for Paul for the case n is equal to 8, q is equal to 6, and k is equal to 1. So let's take a look at this table to understand what is known about this problem. So if you have 0 lies, that's the perfectly true, perfect information game. You know that Paul wins if and only if n is at most 2 to the q. And I'm sure that you've solved this problem on your own, and the attribution is more folklore than anything else. And now assume that you're allowed, or rather Carol is allowed, to commit k full lies. So that's the X channel. Then it turns out that Paul wins if and only if n is less than or equal to, and I'm putting a 1 plus little o of 1 here because actually on the bottom here, instead of q choose k, the combinatorial coefficient, the binomial coefficient, I should have a sum of binomial coefficients. So that's what 1 plus little o of 1 means. It's almost true, but not exactly written that way. And it's not written that way because it was just easier to represent it this way, but it is known exactly. So it is known that n has to be less than 2 to the q over roughly q choose k for Paul to be able to answer. And the attribution of this result is Rennie, Ulam, Berlekamp, and Spencer, a series of papers. The paper that put the cherry on the cake was Joel Spencer's Ulam's problem with a fixed number of lies. Okay, but now assume that instead of full lies, we allow only for half lies, the Z channel. So if she has to say no, it's a truthful no. If she says yes, it could be a lie. Well, it turns out, and this is why this is called a half lie, it turns out that a half lie is about as bad as half a full lie, meaning for each one of these lies, you have an additional factor of 2 from multiplicative factor of 2 from the answer you had before when you had full lies. So half lies are worse. Sorry, half lies are, my bad. A half lie is only half as bad as a full lie, which means that you can do more with Q questions. You can see that the difference between this expression here and this expression here is of 2 to the k. And that means that with Q questions and k half lies, you can do about 2 to the k times whatever the number was before, and you can do more. You can distinguish among 2 to the k more, a factor of 2 to the k more numbers. For k equals 1, this was solved by Cicalese and Mundici, and for other case, it was done by myself and Joel Spencer. And like I mentioned, you can generalize this to more types of errors, to a general channel that has more than 2 values, binary values. And the answer will be roughly like this. There'll be a 1 plus little o of 1 here, which I left out because it wasn't fitting properly. But essentially, you can find asymptotics for all of these in terms of the for n in terms of q and k. Okay, but many other variants of this game have been studied. The 2-batch strategy, for example, which says that instead of asking questions adaptively, meaning every question depends on the answers that she's given so far, what if you ask a first batch of questions all at once, then you hear the answers, then you ask a second group of questions based on the answers that you've heard, you hear those new answers, and then you decide. So instead of asking, waiting for her answers after each one of your questions, you just do all of your question asking in 2 batches. Turns out that's also answerable. What if lies have costs associated with them and Carol has only a finite line of credit, so to speak? And what if the costs change over time? Some progress has been made in this direction as well. another very valid question is, what if Paul doesn't know what channel Carol is using? That is, when and how she can lie. Can he, in addition to finding the number, can he also figure out which channel she's using? And so on and so on. So all of these questions have merit because they relate to this problem of actually bit transmission over a channel. How do you decide how many extra bits to send over to recover, to make sure that the correct message is recovered? So in conclusion, what I wanted to let you know is that playing games and playing fairly simple games with slight twists can lead to actually solving important problems, or it can give us a glimpse of what is needed to solve those important problems, like in coding theory, but not just in coding theory. I mean, I think that Dana before showed this beautiful idea of tiling, which is also, you can also think of it as a game. How can you, in many ways can you tile, right? So game playing is very, very important to mathematical research, to research that relates to many fields of computer science, engineering, and so on. So I want you to keep playing and thinking of ways to be efficient, to find algorithms that will allow you to win perfect information games. And now, just to give you a little bit of trivia, because I've been talking about Paul and Carol a lot in this talk, why Paul and Carol? Well, Paul has been chosen in the community to denote Paul Erdős, which of course, mathematician extraordinaire and father of many combinatorial branches. Some people would say that he is one of the people who founded theoretical computer science. So he's the ultimate questionnaire, and one of the things that most people, I would guess, have heard about him is the Erdős number. Every mathematician has an Erdős number, and the smaller this Erdős number is, the closer you are to having collaborated on a paper or on a project with Paul Erdős. And Carol is an anagram for oracle, which of course is well known for offering foggy and obfuscated answers. So that's why we used Paul and Carol in this presentation. Okay, so that's about it. And I thank you for your attention, and I'm looking forward to answering your questions. And I guess, how can I stop? I'm going to stop the share now. Okay.
Okay, thank you so much, Ioana. That was really nice. I really enjoyed it. And yes, students, if you have questions, feel free to pose them in the Q&A box, and I promise I will ask them of Ioana, Professor Dumitriu. I first met Ioana when she was an undergraduate in college at NYU. So she was just a couple of years older than many of our Math Prize contestants. I was a faculty member at NYU at the time, and she was becoming well known. She made the New York Times for winning the Putnam exam, and we all knew that she would be a star someday, and indeed she was. So I have a couple questions for you. Let's see. So speaking of things like the Putnam exam and Olympiads, I know you did participate in math competitions as a high school student, college student. What do you see as the value of those competitions? Do you find that it was beneficial in your journey to becoming a mathematician?
I would say yes, tremendously. Now, I want to emphasize that being beneficial is not the same thing as being necessary. So we all know that there are many, many mathematicians who did very well without having participated or done particularly well in high school and college competitions. but at the same time, I can say that it benefited me personally a lot in two ways. One of them was that, well, three ways really. One of them was that I got exposed to a lot of math early on, and I found out I liked it and I wanted to learn more of it. And it was a lot of math that wasn't necessarily immediately available to me in high school classes. So that's one. The other one was that I learned a little bit through trial and error. Just like Dana said before, that putting in more effort will yield better results. So it's not a matter of knowing right away. It's not a matter of being born with a certain kind of talent or knowledge. It's a matter of really putting in the work and the hours, and that if you do that, it will show. So that's the second thing. And the third one was I eventually started building confidence. Just like Dana, I started out by noticing, okay, so there were a lot of kids who seemed to be a lot better than me. In particular, they would come out of tests and say, I did everything perfectly. And I would come out of the same test knowing I did maybe 2.5 problems out of 4 or something like that. And I was honest to myself. And so I would hear them tell me how much better they had done. And then in the end, at the end of the day after the results were posted, I found out that many of them had actually placed beneath my spot. And so I learned that, one, it's important to know where you are and what you know and what you don't know. And secondly, don't listen to others. Just do what you can and work as much as you can and do your best, and that will take you there.
Okay, good advice. Let's see. So yesterday, my wife ran a panel for our Math Prize alumni, students who are, gone back college or beyond, and she had some questions, and I'm going to borrow one of them from her. Let's see. So who or what inspired you to learn math when you were younger? It's a multi-part. Did you ever find yourself the only girl in the math club or feel like you were the only girl you knew interested in math questions? Did that bother you? If so, what did you do to motivate yourself, persist, or remain confident as a girl?
Those are great questions. So let's see, what motivated me? I am a little bit of an outlier in that my parents are both, or were both, my dad passed away, academics. And so I grew up as an only child in that family. There didn't seem to be too many options. I kind of knew that I was going to go to a university and maybe do a PhD. And it seemed that I was, I was thinking that I would become an academic eventually. But I was a fairly lonely child. I did not interact well with others. I didn't have many friends. And so around 4th, 5th, 6th grade, when I discovered this one thing, which was math, that I was really seemed to be good at and enjoying and learning more about, and started attending math circles and going to Olympiads, something just clicked with me. And ever since about 6th grade, I did not consider doing anything else but math. But I'm sure that this is an outlier situation. Generally, people figure out what they want to do closer to high school or college. Now, is this good? Well, to a certain extent, it has helped me because it helped me be very focused on what I wanted to do. On the other hand, sometimes I wonder if in high school or college, had I explored more, had I been more open to, say, going into computer science, where would I be now? So in a sense, narrowing the focus helps it be more intense, but at the same time, it closes off some possibilities. So that's something that one has to keep in mind. Now, with respect to the other questions that you asked, was I ever the only girl in the room? Yes and no. There was, when we started out, so I grew up in Romania. Being good at math and physics was, of course, very pushed by the communist government that I grew up under. And so in 6th grade, when I started really getting into contests and competitions and math circles, there were a number of girls who were participating. I think about 40% is probably right. And then they started dropping out. In particular, in high school, the numbers dwindled. And I remember that the answer to this, because I asked one of my beloved and very much respected math teachers why he thought that this was the case. And he said, well, 2 things. One, in high school, girls start being interested in more than just one thing. And secondly, they discover boys. And I remembered thinking that there's just something not right about this. This is not why it's happening. But I do remember that by the end of high school, I was one of very few girls who are still participating. To a certain extent, like Dana said before, I'm sorry, I have to keep on repeating what you said, because my experience is similar to yours. To a certain extent, this has helped me, because being the only or one of the few women in the room meant that everybody knew me. And so later on, I could go and talk to people, or if we met at university or in grad school and so on, we just clicked again. There are potential benefits to this. But at the same time, you've got to try and ignore that a little bit. And I'll offer another little anecdote on this, which was that when I was in grad school at MIT, there were a number of women in my year in the applied math batch, and we were attending this SPAMS, the seminar for applied math, simple persons applied math seminar, which was a great way for graduate students to present to each other interesting problems that they were working on or that they were interested in, and learn how to give presentations, essentially. It was extremely useful. And afterwards, there was and this was one of the reasons why it was so well attended, I suspect, in addition to being very interesting, it was that there was a dinner was provided by the MIT Applied Math Committee. And so I remember going to SPAMS one, I think it was Thursday Thursday evenings, I think, and attending the talk and going afterwards to dinner in the lounge. And at some point, one of my good friends came to me and said, "Ioana, look around the room. Do you notice something?" And I looked around the room. I didn't know what he was talking about. And he said, "Well, I was thinking before you actually walked in to the seminar that there were no women there." Then I looked around the room again, and it was true. I was the only woman in the room, but I had not noticed that until he had pointed it out. Funny thing is that as I grow older, I tend to notice these things more. And I have benefited tremendously from having mentorship by strong women at every level of my professional career, including as an assistant professor, as a postdoctoral fellow. It was, and later on, when it came to balancing my professional and my personal lives, it was great to have a group of women who were at my level or maybe a little bit older to kind of like guide me through it. It's not easy. So representation is important.
Great. Well, thank you for that. And by the way, I've been posing these questions to Ioana, but Dana, if you want to chime in, you're welcome to also. Let me pose another question. Ioana, would you recommend an academic career to the students who are listening right now?
Absolutely. There's great freedom in an academic career. I was thinking that I can do more or less what I want. I can work on my own schedule. Right now, that's particularly helpful because, you know, with the pandemic and having to homeschool two young kids, if I didn't have that freedom, I don't know what exactly I would be doing.
How old are your children?
So the younger one is 5 and the older one is turning 9 in a month. So yeah, they're young.
Yes.
It's not easy right now, but it's also the fact that you get to interact with a tremendous number of people, and you can, from a perspective of a teacher, you get to see these kids come in and grow and learn and blossom. And later on, when they come back and they say, oh, I'm in graduate school now, and I just had a question for you. I was wondering, you know, if you can give me advice relating to this. Or you see them later on when they're faculty members, or they, those are the people that you generally see at conferences. And you feel like, I'm so glad to have known you and to see you and how you've developed over the course of these years. And so that's on the teaching and interacting with people and making a difference, I would hope, side. And then on the research side, I can really choose my own projects. I enjoy doing many things. I have had very broad interests, and I enjoy being able to have broad interests. I mean, I enjoy not being able to, you know, I mean, not having to narrow my focus and look at just one thing, or, you know, with tangentially other things, maybe for the rest of my life. And from this perspective, I've also been seen in pretty much every department I've been in as kind of on the border between pure and applied math. And so that allowed me to interact with people from both sides and serve as a conduit, perhaps, and collaborate with people from different departments, because there are so many departments in a university where math is being done. We had, when I was at University of Washington, we had this group that was called Math Across Campus, which was bringing together mathematicians essentially from all, from a lot of the departments around campus. Math is so powerful and so influential. I think being a math academic is a great place to be. And, you know, computer science is too. So I would say that from this perspective, they're two very core fields that allow you access to a lot of other things.
Okay, that's wonderful. I think maybe I'll conclude with one last question, but first I will pass on a compliment from Dana, who says, speaking of the fun of watching someone flourish, I've heard of Ioana since she was the undergraduate to watch. Several people told me to pay attention. Yeah, so we all agree that you are stars since we heard of you when you were like 20 years old.
Thank you.
So let's see. I know you said that you grew up in Romania, and meanwhile your children are being brought up here in the US and now in California. I wonder if you have a sense of the difference in math educations between Romania and the United States, maybe advantages and disadvantages.
So it's an interesting question, particularly because the system that I experienced is not exactly there anymore. So I grew up under communism, which meant that a lot of the things that are available to my children now were not back then. I had no video games. I had the movies that were running on the big screen cinemas were not really watchable. They were propaganda mostly. I read a lot, and it was easier to focus on learning and doing math because of that. There were fewer distractions. And like most communist governments, they were trying to push forward, particularly talented kids in a lot of disciplines, and try to streamline them toward STEM careers and the like. So there was a lot of infrastructure relating to that, which I think now is a little crumbling, but it's still there because traditionally it's been there, and so you can push it. Once a tradition is being created, it's easier to perpetuate it. But what I noticed, and I think that I'm trying to do the same with my kids, but it's not necessarily as clearly pushed forward here in the US, is this idea that you really should push children, that they can actually learn more than I think we give them credit for. So my older son is in 3rd grade right now, and I mean, he might be an outlier, but he can learn a lot more than what he's being given in school right now. But the good thing is that I've noticed there are a lot of math circles and math classes that he can take outside of his schooling that I'm going to start pushing for him, because exactly, again, like Dana said, what I've been taught really well by my parents is that you should go as far as you can. And so that's one thing that I want to emphasize as well. I mean, sometimes it feels like it's great to make sure nobody falls behind, and that's a great aim, and it should be continued. But it would be also nice to see people being pushed a little bit more to push their envelope, so to speak. Mm-hmm. And that's something that I'm going to have to compensate for, because I'm going to try and implement some of the axioms of education that I grew up with.
Okay, super. Yes, and since you're in San Diego, I believe the Art of Problem Solving has their headquarters in San Diego, and I'm sure they have a math circle and perhaps other classes, both in person and online. I know many of our Math Prize girls here have taken classes online with them, and it's helped. Anyway, I want to thank you, Ioana. Wonderful job.
Thank you.
Thank you again. Thank you, Dana. And I am ready to turn things over, but students, thank you for coming. Thank you for attending. There's just going to be a final remark from Maria.
Dr. Dumitriu, thank you for telling us the truth about playing 20 questions and showing the connection between a game and error detection. But I also want to say thank you to all our speakers for proving that smart people know they know a lot, and that really smart people realize how much they have yet to learn. Unconventional, unusual, unfamiliar. You've heard these words to describe most of 2020. These words also describe uncharted territory in math, science, technology. The fascinating studies you will pursue and the amazing work you will do will have that unconventional, unusual, unfamiliar feel until you start breaking down large problems into small ones, until you make progress in your field. Then you can share your insights with the world and make it a better place, be a mentor to those who come after you. Congratulations on your accomplishments so far. Good luck for all your future endeavors. The world is counting on you. No pressure. This concludes the Advantage Testing's Math Prize for Girls events for 2020. Please look on the Math Prize website for a link to the recording of today's ceremony. Thank you and be well.